we switched to another demo site of the project. So now we are in Bordeaux, France. The work I present here is about modeling, and the goal is to have a model that well describe the dynamic of the envelope to estimate the thermal load of the system, and also to make some comparison of what are the buildings and the system before retrofit and after retrofit with the geofit system. So what was done for this demo site is to create a model of this building that is a building in Bordeaux with students inside. So yeah, as it is mentioned here, we perform some tests to create the model, and at the beginning of the project, the goal is to help for sizing of the equipments, so the ground source heat pump and also the ground heat exchanger. Also to make the comparison between before and after retrofitting, thanks to the model, by simulating 1 year with different conditions and defining some KPIs and making comparison. Maybe also adjusting some piloting rules of helping in the design or to create the installation. So the steps in this work are the following. First, to create the model of the existing system and the existing building, and calibrate this model with measurements. And after we reply, maybe it's not the topic of the today webinar, but we replaced the production part by the installation, the geofit system that is now installed in this demo site. So the ground source heat pump and the heat exchanger. So switch the slide. So here is a view of the layout of the building. We put some sensors inside this building. So sensor to know the temperature, so the thermal behavior, to catch the thermal behavior of the building. Sensor about windows opening, also doors opening. Some sensors to catch the solar heat flux on each orientation. There are the sensors in red here. Also the temperature of the fluid, because in this room there is a floor heating system, so we want to know what is the temperature, the input and the output temperature of the floor heating systems. And also movement sensors to know something about the occupancy. So what was done is to perform some measurement series to make the validation or the calibration steps of the model. So first we have to create this measurement series. So we perform several thermal excitation. The goal is to catch the dynamic of the building and identify the parameters of the model that I will present after. So as you can see here, we force heating or cooling. So the goal of this method is using forced tests, and this allows to avoid long campaigns. So you can see here in this true graph with only 1 week we can learn from the behavior of the envelope and use this information to make the calibration. So, for instance, here you have some stress scenarios. So we force the heating. In this one, the night we make some cooling, and during the day some heating. And in this one, there is only cooling. So it's kind of some tests, some forced tests. And after we use this data for the next step to calibrate or identify the parameters of the model. Oh, sorry. So the model, as I mentioned, is this one. It's based on electrical analogy, so it's quite simple. Only 4 capacity, so 1 for the air, 1 for the floor heating, 1 for the external wall, this one, and 1 for the inner wall. And here you have several power inputs, so the power of the air handling units, the power for the solar, the fine coil units, and also this term is the internal gains due to occupants. So the steps are the following. We define a first model with some parameters here. So in fact, these parameters are the value of the capacity and thermal resistance in the RC model. Before doing the calibration steps, we first perform a sensitivity analysis to define what are the models, what are the parameters that are important, and the one are not important. We can fix their values and only perform the calibration steps on the important parameters and not the others. So the second step here, some parameters are fixed and the others are identified. So we use a calibration method. So there is an optimization process that find what are the values of the parameters that minimize the difference between the output of the models and the measurements. And at the end, we have the elected model with the set of calibrated parameters that are the best combination that minimize this gap between model and experimental. It's quite classical approach. But at the end, we have this model calibrated that correctly describes the behavior of the building. So the next step before using this model in the overall model with systems, we just want here to check if this model is okay or not. So we use true others campaign to validate this model. So we can see here through 1 month campaign, and we check the results compared to true sensors. So the model in blue and true sensors in black. And we can see here that the model it's okay for us. So the level of accuracy it's quite good. There is no big errors, and the major part of the time the error is less than 1 degree, so it's suitable. So we can use this model after validation for the next step. I mean, here we combine this envelope model. So if we look here, in fact, the previous slide are talking just about this part, the envelope. And now we do the same thing for the systems. So in the building, there is a floor heating system. There is fine coil units that provide heat. There is also air handling units that there is no link with the geofeed system, but we have to model it. And we have the gas boiler, that is the production system before the retrofit. So in fact, we made the same approach with the system, and at the end we connect all together the envelope and the system to create this big model in the Modellica environment. You can see here the RC model. In fact, is inside this brick, and the system here that are connected to the buildings. Also the heat production with the gas boiler. And as input of this model, we have the weather conditions, so outdoor temperature, the solar gains, the internal gains with the occupants, and also the set points. So we define the schedule of temperature set point. And as output of this model, we have some indicators about energy consumption, the power, what is the air temperature in the room, the level of comfort. So yeah, several indicators. And thanks to this model, we can now predict or simulate what is the thermal load to estimate the power demand of the envelope. So you can see here the floor heating system, the power load, measurement versus model, and we validate what happened in terms of power demand for the floor heating system, for the fine coil units. So there is the two systems in the room, and also the air handling units. So yeah, this is the model before the retrofit. So here the production of the heat is due thanks to the gas boiler. But the next step, as I mentioned at the beginning of the presentation, is to have the same model, but of the building and the system after retrofit, to make comparison on the basis of the same KPIs. So I put here a screenshot of the model after retrofit. So here I only replaced the production part. Before it was a gas boiler. Now we have the same model, but with the geofeed system. So the ground source heat pump and also the different ground exchangers, so 2 borehole and 2 earth baskets. And we can directly, with these 2 models, make some comparisons, some tests, and predict what are the performances expected with what are the improvements thanks to the geofeed system. So yeah, it's what I want to present you. Maybe this part is not the topic of the today webinar, but what is important is this part here. To before doing this, we want to correctly estimate what is the power demand of the building, and that was the things I presented before. I think it's my last slide. Yeah. So if you have questions, don't hesitate about modeling or other thing. I can answer.